So let's think about Quarkus. Very small and very fast Java. My name is Peter Palaga. I'm Slovak living in Czech Republic, but about 10 years ago I lived in Berlin for a couple of years. And quite exactly 10 years ago I got my master's degree on Technical University Berlin. And I'm very happy to be back after so many years. At the moment I work at Red Hat middleware. I spend the most of my time by developing and maintaining Red Hat Fuse on EAP and Wildfly Camel, which is actually the same code base. One of them is the open source project, and the second one is the product you can buy support for. And in the past, I did the same thing for JBoss EAP and Wildfly. In my free time, I like hacking in build tools, such as SourceTabs, which is a tool for source dependencies in Maven and Gradle. It allows you to declare your dependencies in terms of Git commits or tags, rather than some sort of released artifacts that are available on Maven Central and so on. Except for that, I have written Maven and Gradle plugins for editor config. We will start with a very short demo. And then I will explain what is Quarkus in general, and then I will try to explain some internals, how it works inside. And if you still have time, I will show you some more demos. So let's have a look at the demo. I hope you can read this. Can you read this? You can. So here I have built the project already because it takes about a minute. And I didn't want to bore you at the very beginning. It is a very simple application having just one REST endpoint. And let's have a look what it has built. It has built a native executable, as you can see on the X in the output of ls command. The native executable is just 19 megabytes big or small. Is this nice? It is. Let's have a look if it works. It works. Have you seen how fast it started? Let's try it again. And again. Yeah, it's really, really fast. Does it work? Yes, it does. How much memory does it spend? It spent about 13.5 megabytes. Is this nice for a Java web application? Yes, it is. Good. Take this as a small teaser at the beginning to keep your attention and to make you curious. What is Quarkus and how does it work? So first the name. Don't laugh at the name. I know it has very funny connotations in German, but not us is the hardest problem in software. The naming is the hardest problem, and this is the result. So, but it's not that bad actually in German, is it? It will work, right? The main thing is that Quarkus itself is useful, not the name. To classify it in general, It's a toolkit and framework for writing Java and Kotlin applications. It's a toolkit in the first place because you, as an application developer, will typically use Quarkus as a part of your build workflow. You are not supposed to depend on Quarkus artifacts or use Quarkus annotations unless you do special things. Okay? It's also a framework because in extreme case you will have to use Quarkus annotations, but it's more like framework for people adding support to new libraries. Okay, so as far as you are a Java developer, it's a tool for you in the first place and not framework. So the input for Quarkus tooling are compiled Java classes. The output is an optimized jar that can be run on a stock JVM, such as OpenJDK, or it can be passed to GraalVM, which then produces a native executable out of it, like the one we have seen in the demo at the beginning. Okay? So there are two modes, the JVM mode and the native mode. JVM mode is much faster to compile, to produce, offers faster feedback, so as long as you are developing, you will probably prefer using JVM mode. And when you are done, and when you want to package the application into a container, into an image, you will probably produce the native executable only then, at a later phase of your development. So if I said that you are not supposed to use it as a framework inside your application code, what else are you supposed to do then? How are you supposed to do it then? You are supposed to use existing standards, such as the classical EE standards, servlets, JAX-RS, JPA for persistence, CDI, transactions, bean validation, and so on. Or you can make use of these newer standards, the MicroProfile standards, for the new fancy MicroProfile things like health, metrics, tracing, reactive, and so on. So except for the standards, there are frameworks and libraries implementing those standards that you probably use already today, like Hibernate or RESTEasy. But there's more there to it. There's Jaeger for tracing, not directly Prometheus, but there's OpenMetrics from MicroProfile, and the implementation used is SmallRye. There's some support for Apache Camel and Kafka. There's a client for infinite span cache. And there's Vertex for reactive. This means that you can use both imperative and reactive styles in your applications however you prefer. Quarkus was designed to offer as much developer joy as possible. So because of the known standards and libraries and frameworks, it should be very easy to start with. There's a development mode where you start a daemon, a continuous build that is watching changes in your workspace. And when you hit your endpoints or your application, it will recompile during the request. And because it's so fast, you will not notice that this is compiled. And I hope you will love this. There's Java or Kotlin, there's Maven or Gradle, and there's JUnit 4 or 5 runners. This is actually the main motivation for Quarkus. If you ever run Java in a container, you probably know that Java images are quite big. And we want them to be small, because we want small images that are easy to push, and that are easy to move around between registries, and that are also fast to deploy. We want fast boot time. Why? Because we live in time of serverless, where there are cold starts. And if you are able to start a Java application within microseconds, it's actually perfect. And we want a low memory footprint, because for the given amount of RAM, we want to be able to run as many containers as possible. Naturally, of course, you have to be able to scale horizontally to make use of this. So, okay, let me show you some numbers, but first, let's speak about how we should measure memory. You certainly know heap size and metaspace and things like that are useful in Java. But what matters in the container space is the overall total amount of RAM consumed by Java process. And this number is called RSS, which means resident set size, and it can be output, for example, by the ps command. So given this method, let's have a look at some numbers. We will compare first the very simple REST application that I have shown you at the beginning with just a single REST endpoint. And we will compare it for Quarkus in the GraalVM mode, in the native executable, then in the JVM mode, and we will compare it with traditional cloud-native stack. So the numbers are like this. Quarkus on GraalVM can run with as less as 13 megabytes. If you run it in the JVM mode, it's a bit more, but it's still around a half compared to the traditional cloud-native stack. If you compare the cloud-native, the traditional one, with this one, it's about a factor 10. Nice. If you add JPA with Hibernate, the numbers look a little bit different, not as good, but still quite impressive. The ratio here is about 6 times better. Okay? Let's speak about the boot time. Modern frameworks and application servers use lazy initialization. And what it comes to when we speak about the boot time, they report themselves as started even before all the classes are initialized that are needed to serve your requests. So what matters in the end is the time to first request. How can such a thing be measured? Quite easily. You just need to output a timestamp to the log at the beginning of your endpoint handler, right? Then you start your request producer. This one is 100 times a millisecond. Then you echo the console timestamp before starting your application, which this is the echoed timestamp, and this is the last one, which is the one that we have output from the endpoint handler. And the simple subtraction of these two gives you the number you are interested in, which is the number of milliseconds to the first request. Okay? The time needed to handle the first request to send a response is not there. It's just the beginning. Okay? But it includes all classes needed to handle that request, which means they need to be initialized. So given this metric, let's compare the same three things. Again, for the simple REST application, Quarkus can boot in 14 seconds, under 20 milliseconds, exactly. In the JVM mode, it's about 750 milliseconds. And with the traditional cloud-native stack, it's a few seconds. You certainly know these numbers. Either it's Wildfly or Spring Boot. Again, when we add JPA to the picture, it becomes slower, but it's still 55 milliseconds and about 2.5 seconds. And how many seconds on Wildfly or Spring Boot, you know yourself. Okay? Now let's look inside Quarkus. If you know how traditional application servers work, you certainly know that there are literally hundreds of classes that are needed only during the boot and during deployment of your application. And this, in the first place, takes time during the boot and deployment. And second, those classes occupy space during the whole life time of the application. And this is XML parsers, annotation lookups, and even evaluation of those annotations, management model, and so on. And the main trick Quarkus implements is to do as much of those things as possible at the build time. So all those application, annotation lookups and evaluation and XML parsers are executed at the build time and are recorded and output in form of a bytecode into the optimized jar. And that code is then executed at runtime. This wiring bytecode can be invoked in two ways at runtime. First, and preferred, is to put it into a static initializer. This is first and preferred because GraalVM is able to optimize this further. Okay? But not every piece of code can be put there, because if you access files, network sockets, or other resources that are available only at runtime, you will have to put that code or invoke it from the main method. So this is the overall diagram showing the architecture of Quarkus. This actually resembles very much how Wildfly looks like. Here at the bottom, there are things that have long history inside Wildfly as Wildfly subsystems. For RESTEasy, Undertow, Hibernate, and so on. And all these things work very similarly in Quarkus, but are done at build time. And because this resembles an application container, it's actually called build-oriented container. About extensions. So to support a library or framework that is doing fancy things, you will need an extension. those fancy things include things like reflection and dynamic proxies. We will speak to it, about that later. And Quarkus offers at the moment extensions that you have seen for Hibernate and transactions and so on. But the concept of extension is designed to be general enough for third parties to implement their own extensions. And even Quarkus plans to have a registry of its own extensions and the third-party extensions too. So if you find this interesting and if you want to add an extension that will add a support for your framework or library, you are highly welcome and you should speak to us. So far we spoke about the tooling, Quarkus itself, what it does, how it produces the optimized jar. Let's speak about GraalVM and its further optimizations. So when you nowadays hear about Growl, it may refer to two distinct things. First, it may be the Growl compiler that can work in two modes, either ahead of time or as a traditional JIT compiler inside a JVM, or it can be the GraalVM, an umbrella for many or a number of smaller projects, such as Growl compiler itself, and Substrate VM and some others. Quarkus is using just a Growl compiler and the Substrate VM out of this long list. Okay? So for the rest of this presentation, GraalVM is going to mean just a Growl compiler and the Substrate VM. So Quarkus is using GraalVM to produce native executables. The name for the process is ahead of time compilation. Yeah? In the traditional JVM, the compilation into the native code happens at runtime, and the compilers use some runtime information, and it's called JIT, just-in-time compilation. Okay? This is ahead of time compilation. There are three inputs that are used to produce your native executable. First, your application classes. Second, the JDK classes. And third, some classes from the Substrate VM. You may ask, what is Substrate VM? Substrate VM is something, you don't need to know much about it, that helps you to produce native executables. There are replacement classes and replacement code for the classical OpenJDK there to make things work that would otherwise not work with Growl compiler. What happens during that ahead of time compilation? There's a lot of things happening. There's lots of static analysis happening there that allows lots of optimizations. And there's a closed world assumption. That is, what does it mean? It means that every piece of code that will be needed at runtime is known at build time. And if you think of it, that's quite a strong assumption that will impose lots of limitation of what you can do inside your Java code. And that's exactly why things like reflection and dynamic class loading are either limited or won't work at all. And given this assumption, lots of code can be eliminated. And GraalVM is very good at it. It can eliminate whole classes, fields, methods, or even branches inside your code, if it can make the decision that that code is not going to be used at runtime. Good. If you work manually with GraalVM, this is how you are going to produce your native executable. And the result is what we have seen in the initial demo. Fast start, less memory, and small size on disk. Let's speak about the limitations. There's no dynamic class loading. There's no dynamic class loading. And it means that there are no deployments. No jars, vars can be deployed at runtime. Everything needs to be known at build time. So this means that no traditional application server can be ported on GraalVM. Okay? There are no JVM TI, JMX, and other native interfaces. There are no agents. There's no JRebel, no Byteman, no profilers, no tracers. Why? Because all of these rely in some form on the presence of bytecode. And because it's a native executable at runtime, there's no bytecode. There's no Java debugger. But there's still the native debugger that works, but you have to pay for the GraalVM Enterprise if you want to step through your Java code. Some other things don't exist in the native mode, like security manager, finalize, probably doesn't matter to most of you. I invoke dynamic and method handlers might be interesting to you. You may wonder how Java 8 lambdas are going to work on GraalVM because they use invoke dynamic. And the answer is there are replacements for those in the substrate VM. So there are workarounds. Java 8 lambdas work as usual methods on GraalVM. That's the answer. And this is also a reason why some languages that work on the traditional JVM won't work on GraalVM. Languages like Ruby use invoke dynamic all the time, and they need special tweaks to work there. Okay? So reflection. Reflection works, but need to be registered upfront. And if you work directly with Substrate, you have to do a lot of stuff manually. You can either do it, or I think you need to produce a JSON file that lists all your fields and methods and so on that are supposed to be used via reflection. Very similar with dynamic proxies, resources loaded via get resource, class loader, get resource, all those things need to be registered upfront. Similar for JNI and unsafe. And static init. We will both love and hate this. Because, we will love it because it allows huge optimizations, because all classes are resolved at build time. All static initializers are executed, and a snapshot is taken of the memory that is produced and is put into the executable. And this is exactly why booting native executables is fast. There's no code run. It just takes the blob of the memory, loads it, and it's there. Okay? And that's why the static initializers may not access files and sockets and so on. All those things need to be done via main method. And yeah, this is what I've said. So it's quite complicated to work with Substrate VM directly, because you will have to supply many arguments, take care for it, how it changes inside your code. And that's exactly where Quarkus has the ambition to step in and do all those things for you. So let's, how much time do we have? Who knows? 15 minutes, great. So let's have a look at some things, how you would get started. So these slides contain a link at the bottom, and I have actually posted the slides before the presentation on my Twitter account. That is right here down, so if you want to come back to the slides, you can open them there, and you can visit these links which contain full guide how to do these things. So to start with Quarkus, this is one of the ways that is probably the simplest. There's a special plugin Growl called Create that produces a simple project by default with that single endpoint. And if you call Maven package, it will output the runnable jar. Let's have a look at it in the workspace here. It's not a fat jar, it's a thin jar. And the thin jar relies on, I have to build it, relies on libraries that are there inside the lib subdirectory. So building for the JVM mode is fast. It takes just a couple of seconds, including a simple test. This is fine. It was 6 seconds, okay? Now, the thin jar is there in the target folder. It's just 30 kilobytes, and it relies on libraries in this folder, which is like 20 megabytes or something like that. Thin jars are more practical if you want to use layering for your container image. Good. What's there inside the POM? So there's nothing fancy there. You have to import some BOM so that the versions are managed for you. And there's basically just a single dependency that is not test, the RESTEasy one. The endpoint is a stock JAX-RS endpoint. There is a JAX-RS annotations and outputting hello there. Okay. So development mode. Have I stopped this one because it would conflict? No, I haven't. So development mode. It compiles and keeps running. It watches my workspace, and if I change this, it will update it during the access. So now it still serves hello. So did you see? And when I change it here to hello Berlin, save, nothing changes here. The change comes when I hit the endpoint again. Okay? That was the demo mode with instant feedback. What's next? The native. We have seen how it works. I think I can skip it. Testing. There's a special runner for running unit tests, and the runner will start a thin jar for you before running the test, and you can use RESTassured, for example, to test your endpoints. When I was compiling it here, it was run, and you could see that it works. When I run it again, it will fail because we have changed the output. Yes, it failed. It was expecting hello. And there's a special dedicated runner for testing native executables. It actually extends the test case we had for testing in the JVM mode. And this one just uses a different runner, and the test method is actually the same. I'm not going to run it because it would take about a minute to build a native image again, but the information for you is that you can test the native images too, using JUnit 4 or 5. Okay, what's next? Extensions. There's a special Maven goal for listing extensions. Let's list extensions. The list looks like this at the moment. The list may become longer in about 5-10 days when the next Quarkus version will be released. By the way, Quarkus was started by the end of the summer, 2018. It was publicly announced on March the 7th, about 3.5 weeks ago. And since then, it got about 1,200 stars on GitHub and about 2,800 followers on Twitter, which is nice. What's next? You can also add an extension. For example, Panache. And let's speak about Panache more. Panache is there to make simple Hibernate ORM easy. Because if you use traditional Hibernate, you probably know that you have to put quite a lot of annotations, even for simple things. So Panache takes an opinionated approach. And if you extend the Panache entity, you just have to add the Panache entity annotation there, and Panache does all stuff there for you that it thinks you might want. For example, you can call persist directly on an entity. You can check if the entity is persisted directly on entity, and you don't need to inject the entity manager. The same for deletion. You can list entities using these static methods, and this is by ID and filtered. And all those methods get generated for you automatically if you extend the Panache class and use the entity annotation. This is for counting and filtered counting, and this is filtered deletion and all deletion. Panache offers more for paging sorting, simplified query language. If you cannot leave without data access objects and repositories, all those can be generated for you. Okay, that's about it about Quarkus. There's just a few things I want you to remember from this presentation. It's all the old good Java or Kotlin. It's all those old and good, well-known standards and libraries that you know how to use. But you get the efficiency of the Go language, which makes Java the choice #1 for the cloud and serverless again. These are things, these are links you may find useful when you want to start experimenting with Quarkus. There's documentation and guides for those things I have mentioned and many others I haven't mentioned, such as transactions and health checks and tracing and so on. There's a repository with quick starts, where you will find working examples for transactions and all those stuff. And if you are looking for the most approachable and simplest form of support, please go to Stack Overflow and use the tag Quarkus. The core developers are watching it. If you are interested in writing an extension, you should join the developer list that is not listed here, but you surely find your way to find the email address. Thank you very much.
Thank you, Peter. Hi. One question. Your benchmarks were mostly about startup time and RAM size. So the JVM does optimizations the longer it runs. How does Quarkus compare there? Is it for long-running applications? Because if my server runs for 3-4 days, I don't really care about the first 2-3 minutes.
Very good question. And the answer is yes. JIT inside the C2, just-in-time compiler, inside the traditional JVM, is able to do better optimizations because it's using runtime information, which the substrate VM doesn't have so far. So you can get better response times from a JVM, but at the same time, you can get a better throughput with on GraalVM, because with the same RAM, you can deploy more containers running the same code. So that's the answer. GraalVM on native executables on GraalVM or produced by GraalVM are more effective for this reason. They are more cost effective because you get more power by a bit different means. Because actually, RAM is the most expensive factor, as far as I know, in the cloud, not CPU. Other questions here, for example?
So there is an ongoing trend in using ARM architecture in servers. So does Quarks support producing ARM native bytecode or native code?
So I understand the question, and the answer is this is given by GraalVM, where Red Hat has 1 or 2 engineers. And there either exists support for ARM architecture already, or it's in work and will be supported soon. Supported, like, not commercially, because GraalVM is too new to be supported. There was another question over there.
Yeah, thanks for the excellent talk. I'm keen to have a play with this. It looks very interesting. One of the thoughts I did have is around developer productivity. So I'm guessing there's no things like dependency injection by default. And also just some of the, like using sort of the fat model with the persistence baked into the actual entities. I'm guessing might be a learning curve for some traditional Java developers.
So the answer is no. There is dependency injection. There is a special implementation of CDI 2.0, I think, which is not complete for two reasons. Either features were not implemented yet because it's new, or cannot be implemented at all. For example, there's no session scope because there are no sessions. It's supposed to be stateless, so no sessions. So this is the main idea behind that. You are supposed to work as usual with Java EE standards, where CDI is there. So if you are interested in a specific technology that comes from the Java EE or MicroProfile space, you have to check the website if it's explicitly supported. If it's not, it may still work in the JVM mode, and you still get quite a nice boot times compared to traditional stacks. And if you are very, very lucky, it may work on GraalVM.
So how does it compare to Micronaut, which seems pretty similar in nature?
So
are there any major differences? Or?
The most true and correct answer is try yourself for your use case. The second answer is, and completely biased answer from me as a Red Hatter is that on one hand, I have never used Micronaut, and I would tell you just things I have figured out between yesterday night and today, which is Quarkus makes much more finished impression to me, especially in the GraalVM mode. So for the list of supported things, it simply works. With Micronaut, I think the situation is a little bit more hairy. Maybe you know Micronaut better. And we can discuss it afterwards. And second, I have seen internal benchmarks comparing Micronaut with Hibernate, and it was like this and this. So because Red Hat actually owns Hibernate, it can do Hibernate much better than Micronaut. But the people said that if Micronaut takes the work done by Red Hat for Quarkus, they can do the same well, probably. More questions? No questions? Thank you very much.
Thank you very much, Peter.